All right, let's begin lecture 7 or module 7. This is about hypothesis tests and confidence intervals for multiple regression. The outline for this module or section is that we're going to talk about hypothesis tests and confidence intervals for a single coefficient in a multiple regression model, or a single beta. And then we'll talk about the joint hypothesis tests on multiple coefficients. So, for example, do beta 0 and beta 1 simultaneously equal 0? Other types of hypotheses involving multiple coefficients, so we'll use our tests to determine how to select the best model and how to decide what variables are to include in regression models. So, a hypothesis test in multiple regression. What do I mean by multiple regression? I just mean a regression when we have more than one or independent variable, more than one regressor. A hypothesis test in multiple regression is essentially the same as a hypothesis test in a single regression. So suppose we have a model with k regressors. So we have y regressed on x1, x2, all the way up to xk, where k can equal whatever you want. K could equal 10, it could equal 1,000. So how do we test the significance of beta 2 in this model? The t-stat is going to be just like we had before, except now we put beta hat 2 here, and we subtract off our hypothesis for beta hat 2, or the expected value for beta hat 2. And one note is that a hypothesis for beta hat 2 is just going to be what we guess that the expected value of beta hat 2 is going to be. So oftentimes we guess it's 0, and we're testing whether or not our actual mean of that variable is 0. And we divide by the variance, the square root of the variance of beta hat k, which is an estimate of that is going to be the standard error of beta hat k. That should actually be 2, beta hat 2. This thing is approximately normally distributed with mean 0 and variance 1 by the central limit theorem. The general t-stat is going to be for any k, beta k, it's just beta hat k minus the expected value of beta hat k, or our hypothesis about beta hat k, divided by the square root of the variance of beta hat k. The 95% confidence interval for beta hat 2 is just going to be beta hat 2 plus or minus 1.96 times the standard error of beta hat 2. Same as before. We can generalize this again. The general 95% confidence interval is beta hat k plus or minus 1.96 times the standard error of beta hat k. So hypotheses on beta k can be tested with normal t-stats and confidence intervals because of the central limit theorem. This is super nice. It makes our lives easy. Beta hat 1 and beta hat 2 generally not independently distributed, so neither are their t-statistics. So this is going to cause problems later on when we do joint hypotheses. Let's do an example here. So we're going to estimate test score on student-teacher ratio in two ways. We're going to do our first model is just going to be the single regressor case where we're regressing test scores on student-teacher ratios with no other control variables. So we've seen this model before. And then the second model, we're going to include %EL as a control variable. We've also seen this model, but now we're going to determine how statistically significant our beta 1 hats are in these models. So we're going to compare the single regressor versus the multiple regressor outcomes. Heteroscedastic errors are assumed, so we use robust standard errors for the same reason that we do in the single regressor case. It's just more consistent. We can basically never rule out heteroscedastic errors, so it's always a good idea to use them. And then the coefficient on student-teacher ratio in 2 is the effect on test scores. The effect on test scores of a unit change in student-teacher ratio holding constant %EL in a district. So that's the difference here in interpretation, is that in equation 1 we are finding the average effect of a change in student-teacher ratios on test scores holding nothing constant, but in equation 2, we're finding the average effect of a change in student-teacher ratios on test scores holding %EL constant. So let's construct 95% confidence intervals in t-stats for the first and second regressions, beta 1s in the first and second regressions. So first, write down the null hypothesis. The null hypothesis is going to be that student-teacher ratios have no effect on test scores. In other words, the beta 1 hat is equal to 0. So we write our null hypothesis, H naught, as beta 1 hat equals 0 versus the alternative beta 1 hat does not equal 0. So this is a two-sided hypothesis. Note that we're not saying beta 1 hat is greater than 0 or less than 0. It's just not equal to 0. So let's test beta hat 1 in the single regression model. This one we have presented on this slide. So first let's just do the t-stat real quick. We know that our t-stat is going to be beta 1 hat minus our null hypothesis. In this case it's equal to 0. So that's going to be negative 2.28, that's our beta 1 hat, minus 0 divided by the standard error, and we report the standard error in parentheses under the coefficient, so that's 0.52, and that gives us a t-stat of negative 0.43. Okay, how do we check that against our rejection rule? So our rejection rule, always remember this, rejection rule, let's call this the 95% rejection rule. Reject if the absolute value of the t-stat is greater than 1.96. And so negative 4.38, the absolute value of that is 4.38, and that's greater than 1.96. So we reject with 95% confidence. The confidence interval is just going to be the coefficient plus or minus 1.96 times 0.52, and so if you do this you would get negative 3.299 to negative 1.23. So that's the set of values we cannot reject with 95% confidence. Now let's compare the results with the multiple regression model. So multiple regression test for beta hat 1. So now we're going to do the same test for beta hat 1 in the model with an additional regressor. Turns out it works just the same way. So the t-stat is going to be beta hat 1 minus the null hypothesis, and again we're going to assume that there's no relationship between student-teacher ratios and test scores, so the null hypothesis is H naught beta 1 hat equals 0 versus an alternative beta 1 hat does not equal 0. And so we can plug these values into the t-stat formula. So our coefficient of beta hat 1 in this model is negative 1.1. So we plug that in, subtract off the null hypothesis, and divide by the standard error. Remember the standard error is there. And we get negative 2.54. So again, can we reject this at a 95% confidence level? Is the absolute value of the t-stat greater than 1.96? Indeed it is. 2.54 is greater than 1.96, so we can reject it at a 95% confidence level. Let's construct our confidence interval. We'll get negative 1.1 plus or minus 1.96 times 0.43, and so when we do this calculation we get negative 1.95 to negative 2.26. Notice that 0 is not contained in that interval, and so that's another way to tell that we can reject 0, our null hypothesis, with 95% confidence. But this range that the confidence interval gives us is the range of values that we cannot reject with 95% confidence. So it could be the case that the real relationship is negative 1.95 or negative 2.26. So the results. Can we reject the null in the single regressor case? Yes, we found out we could. Can we reject the null in the multiple regressor case? Yes, we also found out we could do that. What can we learn? We learn there's a robust relationship between student-teacher ratios and test scores. Adding an additional variable does not make the coefficient insignificant. That's what we mean by a robust relationship. So sometimes when you estimate a single regression model and then you add additional variables, the coefficient on the variable of interest might become statistically insignificant with the additional regressors, meaning that the relationship that you're trying to estimate is not very robust, meaning that it's a little bit messy, and so the model doesn't really identify the effect that you're looking for. The single regressor case is also biased due to omitted variable bias, where the omitted variable is %EL. So let's look at that in a little more detail. So here's the omitted variable bias in this problem. Suppose we write the single regressor model as, this is our population regression model. We write it as this, where the error term is EI. And compare it to the multiple regression model. This is again the population multiple regression model. And now the error term is UI. And notice the difference in error terms. In fact, EI can be written as this entire thing here. Why? Well, if we look at these two equations, they're identical up to plus beta 2 times percent ESL plus UI. And so that means that EI is in fact everything that's left off of everything that's left out of this model, model 1. So let's call that model 1. EI contains everything that's not in this equation here. So anything that explains test scores but is not in the equation. So OLS assumption 1 is that the expected value of the error term conditional on the included regressor is equal to 0. So this is the ungeneralized format of the assumption 1. The generalized format is just the error term conditional on the x variables is equal to 0. It turns out that x in this case is student-teacher ratio, which implies that EI is uncorrelated with student-teacher ratio. So we need to make the case that these two things are uncorrelated. But we know if we can substitute in beta 2 times percent ESL plus UI for EI. And so the question is percent EL correlated with student-teacher ratio? So we can, if we substitute in for EI, the last bit of the second equation here, the question becomes a little clearer. Is percent EL correlated with student-teacher ratio? Is something contained in this error term here, EI, percent ESL, correlated with the thing that's included in the model, student-teacher ratios? And in fact it is. We know that there's correlation between percent ESL and student-teacher ratios, and so this does not equal, this line here, correlation between percent ESL and student-teacher ratio does not equal 0. And therefore, we violated assumption number 1. The expected value of the error term conditional on student-teacher ratios equals, we can substitute this thing in for EI. We get the expected value of beta 2% ESL plus UI conditional on student-teacher ratios does not equal 0. So assumption number 1 is violated. So this kind of helps us see the omitted variable bias problem in equation number 1 here. We can make more explicit what's contained in EI. It turns out that percent ESL is contained in EI, and so we can ask the question more explicitly: is the stuff over here uncorrelated with the stuff over here? And we know that it is not, and so we're violating assumption number 1 of OLS. So we get omitted variable bias. And what does this do to our regression equation? Let's just go back real quick and look at the results. Okay, we know that we have omitted variable bias, and so this coefficient, or when I say this coefficient, I'm saying the coefficient on student-teacher ratios in model 1 here is negative 2.28, which is larger in magnitude, absolute value, than the coefficient in this model, negative 1.1. And so that difference there is due to the fact that percent ESL is left out of model 1. That's due to the correlation between percent ESL and student-teacher ratios. So this estimate here, negative 2.28, is biased relative to the true value. And so negative 1.1 is closer to the true relationship between student-teacher ratios and test scores than negative 2.28. That's why it's important to satisfy all the assumptions of OLS. So one thing to note, the t-stats and confidence intervals do not tell us whether our coefficients are biased. So never think that just because something is statistically significant, it is not biased. That's not true. It can be, we can still get statistically strong results even when the coefficients are biased. That's important. The biasness of a coefficient depends on argument. It depends on whether or not you can make the case that, let's write down a model here, whether or not beta 1 is biased depends on making the case that the correlation between x and u equals 0. Are we violating assumption number 1 of OLS or not? And whether or not beta 1 is statistically significant tells us nothing about whether or not beta 1 is biased or not.